In this lecture on radiation, we will see how can we find out the radiation heat transfer from one surface to other surface, where these two surfaces are finite in general. To do that, we already have seen that for that we need the view factor, and how to calculate view factor. Some simple examples we have seen in the last class, that if the orientations are such and the number of surfaces are such that if the independent number of view factors is 0, then without any proper integration we can find out the view factors. But if we find that the independent number of view factors are, say, more than 1 or more than 1, so only for those independent view factors you have to do the integration, and even that integration can be avoided if you can use the proper chart corresponding to that, and the other view factors using the reciprocity rules or the summation rule or the symmetry you can find out. So this concept we have seen in the last lecture. So in this lecture we will see how can we use the concept of view factor to find out heat transfer in the form of radiation from one surface to other surface or the surfaces. To do that, we'll refer first we'll try to refer first this particular slide that we have already discussed in the view factor chapter. Here you can see there are two surfaces, A1 and A2, and their orientations are different, and for that we have seen the rate of heat transfer from 1 that will strike 2 is A1 to 2 can be calculated by integration, double integration over 1 and 2, this quantity I1 cos theta 1 cos theta 2 by r square into dA1 dA2, and the definition of view factor also we have seen, that is 1 by A1 into this particular quantity. So now how can we express this rate of heat transfer from 1 to 2 in terms of view factors, that we'll see. Okay, so let us copy this one and in a new page paste it, so that will help us for the reference. Now as you can see that if you consider only emission, let us consider initially there are two surfaces like this one and this one as shown in the figure. This one is A1 and this one is A2. They are arbitrarily oriented. For simplicity, initially we are considering the surfaces are black surfaces. So we are considering both surfaces are black surfaces. So what is the black advantage of using black surface is that it is only the emission that is come out from the surface. It is only the emission that is coming out from the surface. Okay, and when this emission will strike the other surface, it will be completely absorbed in the surface, because this A2 surface is also a black surface, so everything will be absorbed there. Okay, so if everything is absorbed, so nothing is going to reflect. Since nothing is going to reflect, so there is no chance that something will reflect and come to this surface, so that chance is not there. So everything is going to absorb. Similarly, when something will come from this surface, that is the only pure emission that is going to come from this surface. Okay, so this is what is the advantage of using the black surface first. So initially let us consider the black surface, and if we consider black surface, you know that in that area, if we consider a very small area first, as you can see if you can consider two small area dA1 and dA2, then initially we have calculated dq and then we have integrated over the area, so that we can get the total amount of emission that will strike A2. So we are interested to find out actually Q 1 to 2, and for that what we are doing, remember what is the unit of Q1 to 2, remember we want to find it in the unit watt. Okay, so the rate of radiation emission that will emit from 1 and that will strike A2. And for that, if you consider this elemental area dA1 and dA2, you know that that value is basically the intensity in that direction. So that intensity, if we consider I1, and remember this I1 is a black surface that we have considered here. So this one is basically I1, which is a black surface intensity. So you can also write IB1 into the area which is normal to that direction. So area which is normal to that direction, that is the dA cos of theta 1. So dA1 cos of theta 1. So after that you have to multiply it by the omega, that means the solid angle that 2 will make at 0.1. So that quantity is called omega 21, and that omega 21 is nothing but this projected area which is normal to the distance between them, if that distance is r. So that area is definitely dA2 cos of theta 2. So dA2 cos of theta 2 divided by r square. Okay, so this is what is the expression, that is the small amount of heat transfer that from one dA1 and that will strike dA2. So if you integrate this result twice, if you integrate this result over the whole A1 and A2, then what you are going to get is basically Q12. So further what we are assuming, that assuming this blackbody intensity of surface 1 is uniform throughout the surface. If it is uniform throughout the surface, that means over A1 and A2 this is not going to change, so that quantity will come out of the integration. So if you take it out of the integration, it will be I1 integration cos of theta 1 cos of theta 2 into dA1 into dA2 divided by r square. Now already you know for the total hemispherical emissivity, total hemispherical emissive power, and if that power is E1, so E1 is the blackbody emissive power, because we have considered this one surface is a blackbody, and that is equal to pi into I1. Okay, remember both are blackbody here in this case. So I1 can be replaced by E1 by pi. So you just replace I1 by E1 divided by pi using this result. So if we do that, then we can write this quantity as E1 divided by pi. Okay, so this is what is the quantity, and if you observe carefully the expression of the view factor, you see the expression of the view factor is 1 by A1 into this bracketed term, this integral term, and this integral term exactly same as this one. So this integral term can be written as A1 multiplied by F12. So this quantity become E1, and this integral term here you can see is nothing but A1 multiplied by F12. A1 multiplied by F12, as this is what is the definition of F12 that we have explained in the last class. So the Q12, that means the heat energy in watt, the radiation heat energy in watt that will emit from surface 1 and will strike surface 2 is basically E1 A1 F12. And it is clear that what is this E1? This E1 is blackbody emissive power, and you know that the blackbody emissive power is nothing but sigma into temperature of that surface to the power 4. So if we consider this A1 surface is an isothermal surface of temperature T1, that means everywhere the temperature is same and that is T1, then blackbody emissive power is sigma T1 to the power 4. So E1 you can replace by sigma T1 to the power 4. So this is what is emitting out of the surface. Okay, and since this particular surface 2 may emit something from 2, maybe some energy is emitting, and that will definitely fall in the surface A1, but out of that everything will be absorbed, nothing is going to reflect. Since nothing is going to reflect, so the total radiation emission is on total radiation streaming out of the surface 1 is the only the emission part. There is no reflection part present. That is what is the advantage considering the black surface. Now let us consider that how much this one surface will absorb. How much this one surface will absorb, that will coming out from A2. It is exactly similar way. You can write that from 2 to 1, what is going to come here is nothing but that is A2 into F21 into sigma T2 to the power 4. Okay, so this is what is 2 to 1. So how much is going to come from 2 to 1? So now if you consider only surface 1, and if this is surface 1, if we are interested to know what is the net radiation that is coming out, net radiation means what is coming out minus what is going in. Okay, so the coming out, that we have already calculated Q122, and falling on this surface is Q21. So the net radiation exchange, net radiation that is coming out of surface 1, if you want to find out, that will be basically this quantity minus this quantity. Okay, so if you do that calculation, you see that this will be this quantity minus this quantity. And already we know from the reciprocity rule that A1 F12 is equal to A2 F21. So these two quantity are basically constant. So you can take this quantity along with this sigma as common, and it will remain sigma T1 to the power 4 minus T2 to the power 4 in the bracket. So that is there in the expression here. You can see this is the radiation leaving surface 1 that directly strikes surface 2 minus the radiation leaving surface 2 that directly strikes surface 1 is what is the net radiation. What is the net radiation? So here by Q12 dot means the net radiation. So net radiation will be A1 F12 EB1 minus A2 F21 EB2. Okay, so if you put the value of EB1 and EB2, which are basically sigma T1 to the power 4 and sigma T2 to the power 4, and from reciprocity relation these two quantity are constant, so these two are same, so you just take this quantity common along with sigma, you will get this is the result. So this is the radiation heat transfer in case of black body between surface 1 and 2. This is the net radiation that is coming out of 1. Now consider an enclosure consisting of n black surfaces. That means now we are considering a situation, it is not a two surfaces only. Let us consider this is one surface, maybe there is another surface, there is another surface, there is other surface, and it will form an enclosure. So the surfaces are say 2, 3, 4 like that. Okay, and let us consider this is surface 1, and we may be interested to know what is the net heat transfer from 1. We are interested to know what is the net heat transfer from 1. So net heat transfer from 1, if you want to find out, that will be definitely net heat transfer from 1 to 2, net heat transfer from 1 to 3, net heat transfer from 1 to 4. Okay, so that is what is the net heat transfer from this. That means you have to find out Q1 to 2 net heat transfer, Q1 to 3 plus Q1 to 4. So the net heat transfer from 1 to 2, 1 to 3 and 1 to 4, and all these are net quantities that you have to remember. Okay, so for that you just do this. Already we have calculated what is going to happen between any two surfaces, and that expression you know is that if the two surfaces you consider, say this surface is I and this J surface may be varying from, let us consider the other surfaces, these are say 1, 2, 3, 4 in that way. So the net heat transfer from 1, if you want to calculate, so in that case you have to consider all the surfaces from 1 to n. You see that in place of J, that is going to change from 1 to so here also you can consider Q1 to 1, that is the net radiation that is coming out from 1 to 1. That also you can consider, because you can see that J is starting from 1. Okay, so if it is a plane surface or if it is a convex surface, maybe in that case this quantity might be 0. Okay, so let us find out that what is this value. So this is basically the summation, that rule that you have to apply to find out this quantity. Okay, so till now we have understood if it is a black surface, because here you can see that all the surfaces has been considered as the black surfaces, and that is why the summation rule is applied. Okay, it will be simply sigma T I to the power 4 minus T J to the power 4, because that is the black body emissive power that actually has been considered along with this product. Okay, so now we can extend this analysis to non-black surfaces. If it is a non-black surface, then what is the problem? The problem will be the reflection part will come into picture. Okay, if you just consider the two surfaces, let us consider these are the two surfaces. So from this surface something will emit and that will strike here, and the whole thing is not going to absorb because it is not a black surface. So what will happen? Something is going to reflect back from the surface. Okay, and along with that there is something that will emit from the surface. So what is coming out from the surface, there are two parts. One is what is the emission from this surface, and another one that is the reflection from the surface. And this quantity is now coming here, maybe on this surface. Again, from that something will reflect. So this emission along with this reflection is the again strike this surface. So this is the thing that is going to happen. It is not only the emission, but emission along with the reflection that is streaming out from a particular surface. So this is the situation will happen if it is not a black surface. But what we are going to do is that we'll first assume that if it is a non-black surface, but let us assume that the surface is opaque. Why we are considering the surface is opaque? So in that way you consider that transmissivity is 0, and that means if something falling on this surface, there are two components, either some portion will be absorbed and some portion will be reflected. There is nothing else will be there. So the reflectivity you know is symbolized by rho. So if G is falling, then G into rho is what is reflecting out from the surface. Okay, and the remaining portion, that is G into 1 minus rho, which is basically the absorptivity, that will be absorbed. Okay, this is what is the meaning of the opaque surface. Then we are considering the surface to be also diffuse surface. Diffuse surface means its intensity its intensity is independent of the direction. Okay, so intensity is independent of direction means here the intensity we are considering both reflection as well as emission. So both actually you have to consider in the intensity, that you have to remember. And this quantity is not function of theta and phi. Okay, this is not function of theta and phi. This is what is the meaning of the diffuse surface. Okay, now in case of black surface, we have seen that this intensity that we have considered only the emission, but when we are considering the real surface, that means when we are considering non-black surface, you remember the reflection along with the emission is going to come. Okay, so R plus E intensity that you have to consider, both reflection and emission. And by diffuse, what we mean, this quantity is independent of direction. Okay, does not depend on theta and phi. Third assumption for the non-black surface is we are considering this is a gray surface. By considering gray surface, what we mean that this intensity is also not function of wavelength. Okay, so we are considering that the properties are not function of wavelength. Okay, so with the change of wavelength, it is not going to change. This is what is the meaning of the gray surface. Okay, so as you remember, the spectral quantity epsilon lambda, and this quantity is basically not varying, and this quantity is a constant, and which is basically in terms of emissivity, it is this quantity. Okay, similarly for the intensity, the spectral intensity, which is same everywhere, that is not changing. So basically idea is that this quantity is also not function of lambda. In general, remember this intensity is function of lambda and theta and phi. But when you are considering a gray surface, that means you are considering it is independent of the wavelength. That means for all wavelength the intensity is same, and it is not function of theta and phi. That means it is a diffuse surface. That means with the direction there is no variation. So these are the things that we are considering. Also we are considering the surfaces are considered to be isothermal. So when you are considering a particular surface, we are assuming that everywhere the temperature is same. Let us consider that is T. So it's an isothermal surface. And also the fluid inside the cavity is not participating in the radiation. So if you form an enclosure with this kind of non-black surfaces, so when radiation is coming from a surface to other surface, we are assuming that the medium that is present between the surfaces, if you consider two surfaces, so the medium present between the two surfaces, or if you consider many surfaces, the medium present, that is not participating in the radiation. Okay, so these are the assumptions that we are considering, and based on that we are trying to derive this expression. How can we find out the net heat transfer from one surface to another surface if they are non-black in nature? So for that, you know already that this particular quantity, that is the, if you consider this is a surface, the one portion is the reflected part, that is rho into G, that is, and another part is the emission part. If it is a non-black surface, it is the blackbody radiation multiplied by the emissivity of that surface. So these two quantities are basically streaming out from a particular surface, and the summation of these two, you know, is called the radiosity. Okay, so radiosity of a surface I, if you consider this surface is I, then radiosity of I is epsilon EB plus rho into G corresponding to that surface. Okay, I think this equation is clear. And for the opaque surface, it is only the absorption and the reflection. So absorptivity plus reflectivity is equal to 1. So you can write this rho y, you can write as 1 minus alpha I, right? So rho y you can write as 1 minus alpha I. So again, from the Kirchhoff's law, you know that this alpha I in magnitude is exactly same as emissivity, because you know alpha is equal to same as emissivity. So this alpha is replaced by emissivity here. So I think this equation is clear that radiosity is equal to epsilon EBI plus 1 minus epsilon into GI. Okay, and for the black body, you know that JI must be is equal to EBI if it is a black body. So in that case, reflective portion is not there, emissivity is 1. So in that case, these two will be same, radiosity will be equal to EBI. Now if you consider the energy balance, that means if you consider this is the ith surface, if you just consider this is the ith surface, and from the ith surface the net radiosity which is coming out is say Ji, okay, and something which is falling onto the surface is basically Gi, okay. So Gi is falling onto the surface, and Ji that is coming out from the surface, because within Gi basically the reflection part and the emission part is considered. So what is the net transfer from the surface, ith surface? That is definitely, remember these quantities are all flux quantities, that means their unit is watt per meter square, okay. So these are flux quantities. So what is the energy in watt that is coming out, net energy in watt? That is definitely Ai multiplied by this Ji minus Gi, that is net which is going out, that is Ji minus Gi, and if you multiply it by the area, that will be in watt, that's all, okay. And if you now put the value of a Gi taken from this expression, so from here you can see what is the value of Gi. You see Gi is equal to Ji minus epsilon I into EBI divided by 1 minus epsilon I. So from this equation you find out what is the value of Gi, you will get this expression, and that actually has been placed here. And finally if you simplify, you will get the expression is some quantity Ai epsilon I divided by 1 minus epsilon I into EBI minus Ji. So we are getting this result, okay. So now we can write by making an analogy with the electrical circuit, that how much is leaving, how much radiation energy is leaving from the surface, that quantity, if that is Qi dot, that quantity is EBI minus Ji, as if this EBI and Ji, they are nothing but the potential, okay. So this is basically what is the potential difference, and that divided by resistance. So if this is the equivalent analogy, then what is this Ri? So then the Ri, or this resistance, will be what? If you just simply compare here, you can simply write EBI minus Ji divided by 1 minus epsilon I divided by Ai epsilon I. So it is clear that this quantity is basically then will be Ri. So this quantity is what is the resistance of surface I. So this is called the surface resistance. So this Ri, 1 minus epsilon I by Ai epsilon I, is called the surface resistance, because we are only considering this surface. And you see that why EBI is called the potential, or Ji is called the potential, because EBI is what? Because EBI is nothing but sigma Ti to the power 4. So temperature is what is the reason because of which basically heat is transferring or emitting. So this is like potential. So Ebi minus Ji is basically the potential difference divided by this is the range. This is called the surface resistance. So expression of surface resistance you have to remember, and if you can do that, you can find out what is the value of Ji. Okay, because if you know the surface properties, and then it will be possible to find out Ji if you know the temperature. Suppose you know the temperature is Ti, and you know what is the emissivity, and you know what is the area. That means as you know what is the emissivity and area, that means the geometry and the surface property emissivity, then and then you can find out what is the resistance. And as you know Ti, that means you know what is Ebi. So now simply using this formula, basically you can find out a relationship between Qi dot and Ji. Okay, so that is going to help you. So if it is a black surface, then this problem will not be there and the surface resistance will become 0. If it is a black surface, then epsilon I will become 1 and the resistance will become 0. So Ebi and Ji will be same in that case. But if it is a non-black surface, remember it is the Ji that you have to consider. Now note that the surface resistance to radiation for a black body is 0, that we have just mentioned. It is very important. For insulated or adiabatic surfaces, if the surface is insulated or adiabatic, the net heat transfer through them is 0. Okay, so in this case the surface is called a re-radiating surface, and there is no net heat transfer to a re-radiating surface. So if a surface is insulated, so net heat transfer to the surface is 0. Net heat transfer to the surface is 0, but it is not that this surface is having 0 resistance. The surface having some resistance because of its property, emissivity and the area, but there is no net heat transfer to the surface, or heat transfer to the surface or from the surface, because it is adiabatic or insulated. Okay, so that is why this kind of surfaces are called, if it is adiabatic, with respect to radiation, it is called the re-radiating surface. Now coming to the net radiation between two surfaces if they are non-black, we are coming to that problem now. And you remember the assumptions that we have considered. The surfaces are diffuse, grey, opaque, okay, and uniform temperature. These are the conditions. And again consider the similar situation. So only difference here, you just remember the I, the intensity that we have considered, actually make this one a bigger one. Okay, so I in this expression, as you have seen, we have considered this I is the black body intensity. Okay, so but if it is not a black body, in that case, remember this I consisting of two parts. One is emission, another one is a reflection. So these two parts will be there. And if you want to do this integration, you know that over the whole hemisphere, this quantity will produce nothing but the radiosity. Okay, because radiosity is something, this flux corresponds to both emission and reflection. Because in case of black body, what you have seen, that if it is a black body, and that if you integrate over the surface whole hemisphere, then you will get, it is the emissive power, black body emissive power. Okay, and they are related by pi into this quantity. But here the same relationship, but now you are going to get the radiosity that you have to remember. That's all. Now Okay, so now if you want to uh, calculate the same thing, what you are going to do, you will get a relation that q 1 to 2 will be equal to, instead of I, but remember I, we are considering r plus e. Okay, I r plus e for the surface 1, maybe for the surface 1. Okay, and that we are considering uniform over the whole surface 1, and that will come out of the integration. The remaining portion is same, like cos theta 1 cos theta 2 dA1 dA2 by r square. Okay, and now if you want to replace this quantity in terms of the radiosity, and that relationship exactly similar way, it will be pi. So you just replace by what? This will be radiosity of 1 divided by pi. Okay, and similarly what is the net radiation streaming out of the surface 1, and that quantity, if you want to now express this quantity in terms of this integral quantity, in terms of this integral quantity, now if you want to express in terms of this f12, you see that f12 into a1 is basically this integral. So q12 becomes j1 into f12 into a1. Okay, so this is how much radiation will come out of the 1 and will strike 2. Similarly, how much is the streaming out of 2 and that will strike 1. If we can find out that, then the net from 1 to 2, the net from 1 to 2, if you want to find out, so q12 net will be what? The net will be basically j1 f1 to a1 minus j2 into f21 a2, because j2 f21 a2 is basically what is streaming out of 2, and that will strike 1. So this minus this is what is the net that is coming out from 1 to 2, and that is from the reciprocity relation, these two are same, so it will become a1 f12 into j1 minus j2. Okay, so between two surfaces, this will be the net radiation heat exchange from 1 to 2. So that is between I and j, it will be ai fij ji minus jj. Okay, so in analogy with the Ohm's law, if we want to make, then what is this q? This q quantity is like ji minus jj is the potential difference between 2 points, and that divided by resistance. So the resistance between I and j is nothing but 1 by ai fij. So if you just write this quantity like that, ji minus jj divided by 1 by ai fij. Okay, so this quantity is what is the resistance. So this particular resistance is called the space resistance. So previously we have seen the surface resistance, which was 1 minus epsilon I by ai epsilon I. That was the surface resistance, and here now you can see this quantity 1 by ai fij is what is the space resistance between I and j point, and this is the surface resistance at the surface I. Okay, so now if you can make an equivalent thermal circuit for a problem where 3 or 4 or more than many black surfaces are involved. So equivalent electrical network, equivalent thermal network for the radiation now we can generate. So here you can see one network has been written. Let us consider there heat is interacting between two surfaces only. Say the surface is I, another surface is J. So what is the network? You see that you have to start from as if EBI, then you have to put the from that surface initial resistance will from EBI to JI. Then this is another surface, so from the surface there will be surface resistance, and from then EBJ to JJ. So now between these 2 points J there will be a resistance which is the space resistance. Okay, so this is the equivalent thermal circuit, and through which what is going from I to J is QIJ dot in watt. Okay, so this is what is the basic idea. Now similarly, as we have done earlier, if you want to find out from one surface how many maybe there is an enclosure, maybe other surfaces there are enclosures. If you want to find out that what is the total number of heat, that is what is total transferring, so definitely it will transfer to other surfaces. So from surface 1 it will transfer to surface 1, 2, 3, if there are n surfaces, up to n surface. So you have to apply the same space resistance between 1 to 1, 1 to 2, 1 to 3, like that, and you have to add them all. So this is basically has been done. This is what is from I to J, and this J is now changing from 1 to n. So that will give 1 to 1, 1 to 2, 1 to 3. So the second thing, that is what is the J, that is changing from 1 to n, and the I is fixed. Here we have considered 1, it can be any surface. Okay, so this is the way we can find out the heat transfer from a particular surface. So this is we have already derived this relationship for the space resistance. This one is the space resistance, as you can see, and the combining these two we can write that okay, if the situation is this is a non-black surface, say I, and let us consider from this non-black surface there is an enclosure, maybe there are n number of total n number of surfaces are present, then the equivalent thermal circuit will be like initially the surface resistance, that is what is QI. Okay, so from the surface resistance it is coming out is QI, that has been shown here. What is QI? That is coming out of the surface net from the surface I is EBI minus JI by RI. Then after coming to JI, basically it is transferred to all the surfaces from 1 to n. Okay, so that is nothing but the summation from I to 1, I to 2, I to 3 to all the surfaces. Okay, and summation of that is nothing but what is happening at the node. So these two quantities definitely same. So if you try to draw this equivalent circuit, it is like this. Okay, so there may be n number of surface what is coming out from this node, and here it is what is the EBI. Okay, maybe this is what is JI. Okay, and then the other surfaces are present, so maybe J2, J3, J4, and all the surfaces are maybe present. Okay, so summation of all this, if you do, you will get this summation, and that must be same as what is coming here. So this is what is over the surface resistance. So that is why this heat transfer, that means what is coming here must be going or divided in all these branches. Okay, so that is why this quantity is equal to summation of all this. Okay, so what is the method for solving this kind of radiation network problem? So first of all, that you have to form an enclosure. It is very important to form an enclosure. In the last lecture we have explained how we can form an enclosure if it is not actually an enclosure. Let us consider there are two surfaces. Suppose this is one surface, this is one surface, and we have to find out, suppose, the radiation heat exchange. So what we do, we can form a surface like that and we can join it. Okay, so then this is the third surface, and then we can consider these 1, 2, 3 as an enclosure and draw a surface resistance associated with each surface of the enclosure. It is very important to consider the surface resistance. If it is a black surface, definitely surface resistance will be 0, but if it is a non-black surface, its surface resistance has to be considered. Now connect the surface resistances with the space resistances. Okay, so for a surface, then you have to connect it with the space resistance and solve the radiation problems by treating it as an electrical network problem. So let us see one example and try to understand. So here is a problem of two parallel plates separated by a distance. All the informations are given, and the assumptions we will always consider like diffuse, gray, opaque, and steady state heat transfer. So the problem is that there are two plates as shown by 1 and 2. The dimensions are given, their temperatures are known, okay, and distance between them is known. The question is, you have to find out the radiation heat exchange from surface 1 to 2, or surface 1 to the net heat transfer to the surrounding. This kind of questions may be asked. So how much heat is transferring from plate 1 to the surrounding air? Okay, like this kind of questions may be asked. So here the questions that has been asked is that find the net heat transfer rate to each plate and the room. Okay, so you have to find out net heat transfer rate to the each plate and the room, and neglect other modes of heat transfer like convection and conduction. So how to approach this problem? First of all, you have to form a thermal circuit or radiation network. So radiation network, first of all you have to make an enclosure. So one surface and two surfaces, these two are rectangular plates, parallel plates separated by a distance. So assume the other surface is surface 3, by which the whole thing is now an enclosure. Let us consider it is an enclosure. Okay, so that is 3. So now you have 3 surfaces, and let us consider this surface is 1. So corresponding potential is EB1. What is EB1? That is corresponding to temperature is T1. So this is sigma T1 to the power 4. But this is one surface is not a black surface, so it should have a surface resistance. So put a surface resistance. What is surface resistance? 1 minus epsilon 1 by A1 epsilon 1. As you know, the emissivity and the area is given, so you can find out the surface resistance. Temperature of the surface 1 is given, that means you know what is EB1. So now where you reach is J1, so this is one node. So for the surface 2, similarly, maybe surface 2 is here. Let us consider this is EB2. EB2 means what? Sigma T2 to the power 4. And this is again not a black surface, so put a surface resistance, and you know surface resistance is what? 1 minus epsilon 2 by A2 epsilon 2. Now from 1, and this is 2, and there is another surface which is 3. Now this 3 is what? EB3 is equal to J3. Why EB3 is equal to J3? Because this third surface is an enclosure that we have considering, which is actually not there. So our assumption is it is like its area is very large. Its area is we are assuming that area is very, very large, because this is what is the assumption, and that is why we can consider its temperature T3 is equal to T infinity, and we are assuming its emissivity is equal to 1. Emissivity is equal to 1 consideration means E3 is equal to 1 consideration means we are assuming that it is a black body. Okay, as if we are considering the surface resistance. surface resistance of 3 is equal to 0. Why we are assuming surface resistance of the 3 is equal to 0? Because it is 1 minus epsilon by A3 into epsilon 3. This is actually the quantity, right? But actually this surface resistance is 0. The reason is that this A3 is very, very large. This A3 is very, very large. Since A3 is very, very large quantity, so this fraction is tending to 0. And that is what is actually the reason that we are considering the surface resistance is 0, and that is why EB3 and J3 which are same. Okay, so now heat is transferring definitely from one plate to the atmosphere. Heat is also transferring from one plate to plate 2. Similarly, from plate 2 it is also transferring to the atmosphere. So this will be the radiation network. Okay, and this is what is J2, this is what is J3 or EB3, whatever you call. Okay, and atmospheric temperature is given, so EB3 is sigma T3 to the power 4. So I think the radiation network is clear. The remaining thing is you just consider at each node what is the heat transfer that definitely is equal to summation of heat transfer from all three direction, if you consider, must be is equal to 0 at a particular node. So if you consider node 1, what is the heat transfer? That is the potential difference divided by the resistance. So what is the potential difference? That is EB1 minus J1 divided by the surface resistance. The surface resistance is 1 minus epsilon 1 by A1 epsilon 1. Okay, similarly if you add with that, that is what is considering this direction, this is from this direction, so it will be J2 minus J1 divided by this surface resistance, this space resistance between Z1 and Z2, it is the space resistance, so 1 by A1 F12, or you can write A2 F21, both are same. Okay, plus you consider this one, and that is from 3 to 2, so 3 to 1, so J3 minus J1 divided by 1 by A1 F13, or you can write A3 F31. So A3 is not known, so A1 F13. Okay, and this summation must be is equal to 0. So for the node 1 we can apply this similar way. You just write the expression at node 2 considering this direction and this direction. You just write what you are getting for the node 2, and these two equations will help you to solve for J1 as J1 and J2, because these are the two unknowns only. Okay, so for that you need what? That is the view factors, and by the time you know how to calculate view factors. So for the parallel plates, you know, if you know all the dimensions and the difference between them, with the help of charts you can find out F12. So first from the chart you find out what is F12. Once F12 will be known, then you require F13. So what we can write from 1 to 2 and 1 to 3, so F11 summation rule if you want to apply, and F13, this summation you know is equal to 1. F11 is 0 because it is a plane surface. F12 from the chart you will get the value, so F13 you can easily find out. So you just use that value in here in this expression. Similar way you can also find out F23, and from symmetry you can tell that F23 and F13 will be equal to same. Okay, so in this way you can find out the view factors, and you write this equation. Similarly write the similar equation for node 2, that summation of the heat will be equal to 0. And once you know this J1 and J2, Then to find out what is the heat transferred from 1 to 2, from 1 to 3, that means atmosphere, or from the plates. So for that you just apply this one. This is what is the heat transfer from plate 1, Q1. So what is Q1? Q1 is equal to EB1 minus J1 by this resistance, 1 minus epsilon 1 by E1 epsilon 1. Because J1 you can solve, and EB1, these things are known, so you find out Q1. Exactly in a similar way, find out what is Q2. Use the same formula to find out Q2. Okay, that will be EB2 minus J2 divided by this, that will be E2, Q2. So in this way you can find out Q1 and Q2 separately. And to find out Q3, so how much heat is transferred to the atmosphere, what you can do is that Q3 must be equal to Q1 plus Q2. Remember, this Q1 and Q2 are the net heat transfer that you are considering. Okay, so that is why Q3 will be equal to Q1 plus Q2. So here you can see the equivalent circuit that we have explained. Here you see that how the view factors are calculated, and then individual resistances that you have to calculate for all these in the circuits. And for the node 1, this equation has been written. For the node 2, the equation has been written. You see that J3 is same as EB3, which is sigma d to the power 4. And if you solve it, you will get, you see, the value of J3 that is known. Basically you have to solve J1 and J2. So once J1 and J2 is solved, then you can easily find out what is Q1 and Q2 in watt. Okay, so this is what is done. And finally, to find out Q3, either you use this basic formula, or you can also use this one. Okay, so this is what is the way we can solve problems related to the radiation network. One more problem I like to show you, the similar kind of problem but very common. Let us consider there are two very large plates, say 1 and 2, and assume that these are infinitely long or very large plates, so that the sole heat transfer from 1 is striking 2, or on the other hand which is emitting from 2 is striking 1. That means basically if 1 to 2 is equal to 1, or if 2 to 1 is equal to 1. Okay, so whatever is coming out of 1 must strike 2. There is no other interaction. Okay, but the previous problem we have seen that these two plates were finite, so the atmosphere we have used as an enclosure for the third participant. But here these plates are given very large, infinitely long, so that you can consider these assumptions. So for this one, suppose the temperatures are given T2, T1, properties are given, say epsilon 1, epsilon 2, and you have to find out what is the heat transfer will take place. It's a very simple problem. So you have to simply draw the equivalent circuit first. First the surface resistance, that is 1 minus epsilon 1 by A1 epsilon 1. Then the space resistance, here the surface resistance. So this is what is the simple circuit that you can easily find out, and you can find out how much heat will be transferred from, net heat will be transferred from 1 to 2 or 2 to 1. That you can find out. Simple problem. But suppose the problem is given that there are two such plates, very long plates, and in between there is some other plate, and you have to find out that now how much heat will be transferred from 1 to 2. Now how much heat will be transferred from 1 to 2. Suppose this is the problem. If the third plate is inserted, all the properties are given, say this is epsilon 3, A3, all these properties are given, T3. Okay, and this was T1 epsilon 1 A1 T2 epsilon 2 A2. Let us consider all, maybe having the same area also you can consider. Okay, so how can you solve this problem? So for this problem, what you have to do is that from here you have to draw the circuit. So what will be the circuit? First you have to give the surface resistance, then this is another surface, so here also there will be some surface resistance. In between these two there will be some space resistance. Now from here to here there will be some surface resistance, then space resistance, then again surface resistance. So all these things will be there. So if you write, this is 2, this is 3, and this is 1. So first there will be some surface resistance. So from E1 to J1, then there will be some space resistance up to J3, then there will be some surface resistance up to E3, then again some surface resistance up to maybe say J3 prime, then space resistance J2, surface resistance, and we will come to EB2 or E2. So we have to solve this particular circuit to find out how much heat will be transferred from 1 to 2. Okay, so all the resistances values you can write, the surface resistance and all this, and you know what is E1 and E2. So you will be able to solve this problem. Since all the resistances are in series, so you sum all these resistances in series, like find out what is E1 minus E2 divided by summation of all these in series. You will get Q, that is from 1 to 2, what is the net heat that is going to transfer. Okay, so this is the general technique to solve this kind of problem through radiation network. Okay, thank you.